Angular momentum is enormously important in physics. For example, it's central to all kinds of scattering experiments, and scattering experiments lie at the core of high energy physics. They play a very big role in condensed matter physics. Angular momentum plays a central role in the theory of the application of quantum mechanics to atoms to get atomic structure. So from the very beginning of the subject, it played a very big role. And people write whole books, horrifically, they write whole books on angular momentum in quantum mechanics. So we are going to have to spend a few lectures on it, even though there won't be quite as much physical content. We're building foundations for later work, is what I suppose I should be saying. But we will, on Wednesday, in the next lecture, we will at least be able to do something interesting and useful with angular momentum, so the outlook is not entirely bleak. But I'm afraid today's lecture is a bit on the formal side. So you will recall, I hope, at the end of last term, we talked about operators that generated translations. They turned out to be momentum operators. And we concluded that there must be operators that effect rotations. So there must be a unitary operator, U of alpha, which generates a state like the state you've already got, that generates a state that's the same as the system you've already got, except rotated by an angle mod alpha around the unit vector in the direction of alpha. Right? There must be some unitary operator like this. This is a unitary operator depending on a continuous parameter, right? You can shrink the angle of your rotation down to nothing continuously. It's in that class of unitary operators. So it's generated. We can write it as the exponential of something or other. By putting an I in there, this thing becomes the Hermitian operator. These J's, and because there are three components of this vector alpha, which describes the rotation that you're planning, there must be three of these operators that generate these rotations, and we're calling them, of course, Jx, Jy, and Jz. I said that they are the angular momentum operators, but we haven't really done a great deal. We didn't do a great deal at that time to justify this claim. We have those three operators. They're the generators of rotations, respectively around the x-axis, the y-axis, and the z-axis. Out of them, because they're Hermitian operators, we can construct another operator called J squared as the sum of the squares of the operators. And we have a set of four operators, and we showed by considering what happens when you make rotations around different axes, we demonstrated that these operators must have the commutation relations that J squared commutes with all of them, with all of Jx, Jy, and Jz. But these operators do not strangely commute with each other. They have the commutation relations that Jx, Jy is I, Jz, and similar things, which can be encapsulated in this way, where epsilon ijk is the object that keeps changing its sign, and is zero if any two of its subscripts are identical. So what we want to do now, so that sort of showed the existence of these things. What we have to do in the next section is find out more about these operators and the eigenstates of these operators. We need to justify the claim that these operators really are the angular momentum operators. We need to find, crucially, well, it will turn out that the orientation of something like an electron, well, indeed, the orientation of any quantum system is encoded in the amplitudes to find the possible results, the possible eigenvalues. When you make a measurement of Jx, Jy, or Jz, there will be possible answers. You'll get a number which belongs to the spectrum of that, and the amplitude for that event strangely encodes the orientation of the object. Right? We need to understand about that. So what we want to know now really is what is the spectrum of these operators. You want to know what are the possible results of measuring J squared or Jx squared or Jz squared or whatever, right? So this is what the next spectrum is about. It's about the spectrum of J squared et al., right? These operators. So since the Jx, Jy, and Jz don't commute with each other, there isn't a complete set of mutual eigenkets of Jx, Jy, and Jz. But there is a complete mutual set of eigenkets because of that commutation relation, because J squared commutes with all of its subordinates. There is a complete set of mutual eigenkets of J squared and any one of those, and it's conventional to study, to pick just at random that we choose to have mutual eigenkets of J squared and JZ. So it's just a convention that we choose JZ out of the three things, connected to the fact that Z is the singular axis, is the special axis in systems of spherical polar coordinates. All right? So in spherical polar coordinates, X and Y have pretty much the same role in life, but the Z axis is special. And that's why we choose this one. Okay. So that's what we're going to do. So we're going to say, look, there must be some eigenkets. We're going to label them by beta m. This label is going to tell us how the thing responds to this operator. Concretely, it's going to be this, right? So obviously, we're labeling this ket by its eigenvalue with respect to J squared, and JZ on beta m is going to be m beta m. So the second label in this thing tells you how it responds to JZ. And this is by definition a member of the complete set of mutual eigenkets of this operator and this operator, which the mathematicians have promised us exists. Okay. Now we introduce some ladder operators. We're going to follow a line of reasoning that's very similar to how we got the eigenvalues of the Hamiltonian of a simple harmonic oscillator. We're going to introduce J plus as Jx plus I Jy. So this is a little bit analogous to when we introduced in the simple harmonic oscillator the destruction operator. We said that A was equal to X plus IP. Similar game. So because of this I, this is not emission. It's not an observable. It's a tool of the trade. And correspondingly, needless to say, we have J minus, which is equal to Jx minus I Jy. And we also have that J plus dagger is equal to J minus, all right? So this thing here is the Hermitian adjoint of that thing there, because if you take the dagger of this equation, this dagger goes into this because it's an observable, that goes to minus I, and this goes into this. So these are tools of the trade. Now we find, now we ask ourselves what are the commutation relations? We have that J squared on J plus is nothing but J squared comma Jx plus I J squared comma Jy is nothing, because this vanishes and this vanishes, right? So J squared commutes with J plus, and of course it commutes with J minus as well, right? So this is plus or minus, it vanishes. What does that tell us? That tells us that if you've got if you take J plus of beta m, you use this non-trivial operator on this state, you get some other state. What can we say about this other state? Well, one thing we can say is that J squared applied to it, because you can swap these two over, is the same as J plus beta m. So you swap these two over, then J squared looks at this and says, aha, that's my eigenket, out pops a beta. This is a mere number, can be popped over here, is equal to beta J plus beta m. So when you use J plus on this eigenstate of J squared, you get another eigenstate of J squared for the same eigenvalue, right? Encouraged by that, the next thing to do is to have a look at Jz on J plus beta m. Now, when we swap these two over, well, we want to swap the two over, but of course we can't, so we do the usual business. J plus Jz, I've swapped them over, and then add in what we should have and take away what we're not entitled to. Jz comma J plus, commutator, brackets, brackets, beta m. Now this, we found what this thing was. We found that, oops, sorry, we didn't. We didn't, sorry. I'm getting ahead of myself. Apologies. Right. So that's what we need to. Okay. Well, we're going to find out what this is. We're going to find out what this is. That's the next thing we have to do. All right. So what is jz comma j plus? Well, it's jz comma jx plus I jz comma jy. This is minus I jy from the rule given way up there. And this is minus I. So this is going to be I, this I, minus coming up another I, jx, again from the rule above. So this is going to be minus, this is going to be j plus, because this is, these two i's are going to make a minus sign, cancel this, we're going to have jx, it has to be plus. What the hell's gone wrong here is I've goofed presumably in that x, y. Yes, I've goofed in that, sorry. I'm always bad at this cyclical ordering. So it is equal to j plus. So we take this important result, we stuff it in there, and we have that jz on j plus beta m is equal to, so this is going to be j plus, and jz working on that is going to produce an m times that. So we're going to have an m plus 1 times this. So what does that show? That shows that when you apply j plus to this object, you get a new eigenket of this operator, one which has this for an eigenvalue. So let's write that down. It says that j plus on beta m is equal to m plus 1, is equal to some amount of, which we will call alpha plus, the state beta and m plus 1. Okay. So the point is that what goes in here is the eigenvalue of this thing with respect to jz. So this thing here turns out to be, this shows that it is an eigenket of this operator with this eigenvalue, m plus 1. So that's what should go in there. And this is some constant, this is some normalizing constant. So what have we achieved? When we applied j plus to this state jm, we made a new state with the same total amount of angular momentum, the same response to j squared, but the amount of this parallel to the z-axis has increased. So we have reoriented our system, right? We have here a spinning top, well, okay, some angular momentum along here, and we've moved it a bit towards the z-axis. That's what j plus does. Realigns the angular momentum that you've got. Strictly speaking, it makes you a new state, and this new state has the same angular momentum as the old state, but more of it's parallel to the z-axis. Okay, we could repeat all this stuff. I recommend that after the lecture you do repeat all this stuff using j minus, and you will find that j minus on beta m is going to equal some amount, not to be determined, not known yet, of beta m minus 1. It does the reverse trick. It moves it away from the z-axis, or if you like, towards the minus z-axis. So showing this is precise repeat of what was done up here, except every plus sign gets turned into a minus sign. Okay. Now, we have that the expectation value of, for example, jx squared is equal to jx psi, for any state of psi. So take any state of psi and work out this expectation value of jx squared. It's jx psi mod squared, right? Because if you take the mod square of this, what you're doing is taking the Hermitian adjoint of this, which is that, the Hermitian adjoint of jx, which is jx itself, and multiplying it into this, so you end up with this. And this is the length squared of a vector, so it's greater than or equal to nothing for all of psi. So let's ask ourselves about Jm, j squared, Jm. That's clearly equal to beta, because j squared onto, beta m. So j squared on this produces beta times this. This is correctly normalized, so we get beta. But this can also be looked at as beta m jx squared, beta m, so it's equal to this, plus beta m jy squared, plus beta m jz squared. But this last one here is clearly m squared, because one of these j's looks at this and produces an m times beta m, and the other one then looks at that and produces another m times beta m, and we end up with just m squared. So what have we got? We've got that beta is equal to, what should we call this? We'll call this A, and we'll call this B, is equal to A plus B plus m squared, where these numbers are greater than or equal to naught. In other words, we've concluded that beta is greater than equal to m squared. So there's a problem. We've got an operator j plus, which can make us a new state with m increased by 1, which has, but this new state has the same value of beta. So apparently we can make states with bigger and bigger m for the same beta. And that we've just shown mathematically that that's absurd. Physically it's absurd, because I'm saying that I've got a fixed amount of angular momentum and j plus just moves it towards the z-axis. Well, eventually it'll have it parallel to the z-axis, and it won't be able to increase m anymore. So what truncates this, something has to give, and what it's just like the harmonic oscillator. What gives is that eventually, so series of states of bigger m truncated at beta m max for maximum value of m, such that, how does this happen? It happens because when we use j plus on this state, we get exactly nothing. So what does this mean? This implies that alpha plus equals naught in this particular case. That's the only way we can be stopped from making states of bigger and bigger m, and it's clear we have to be stopped. So we are stopped in this way. So what we have to do now is look at the mod square of this state and show that it's 0. So we have that naught is equal to mod. So the mod square of this is going to be this Hermitian adjointed times j plus dagger, which is j minus, times j plus times beta m max. Right, so this thing here, this is j plus dagger, which is appearing here, and I pointed out earlier on that J plus dagger is J minus. So let's have a look, see what we've got here by staring inside. So this is going to be, I don't need the mod square, that's already taken care of. So this is beta M max Jx minus I Jy, Jx plus I Jy, close brackets, beta M max. So we multiply this stuff out. And we get Jx squared plus Jy squared. And then we have a minus I Jyx, the plus I Jxy, so we have plus I commutator Jx comma Jy. Well, when we've got this much of J squared, we might as well have the whole of J squared. So we write this as beta M max J squared minus Jz squared, right? So we add a Jz squared and take it away again. And this, of course, is I Jz. So along with that I, we get minus Jz, beta Mx. And now we're in Clover because we know what every single one of these operators produces when it bangs into that. So we can evaluate this. This, of course, produces a beta. So this is going to produce a beta times this thing. Then this thing will meet this thing and produce 1. So I only need to write down beta. This Jz will produce an M max times this thing, which will then bang into this thing and produce a 1. So I have a minus M max. And this one is going to produce M max squared, also with a minus sign. So in fact, let me write this as, oh, never mind, M max squared. So this is more conveniently, right. So what do we have? We have that nothing is equal to this stuff, from which it follows that beta, we've discovered now what beta is in terms of M max. It's equal to M max brackets M max plus 1. So if we apply J minus to beta M, I claimed that this was alpha minus beta M minus 1. So M will start, let's imagine M starts off positive. As we take units from it, it's going to get smaller. And if we keep going, presumably it'll become negative. And M will start to be a negative number of growing magnitude. But we still have this condition that M squared has got to be less than, M squared has got to be less than beta. So this series of operations has got to terminate as well. So series of kets with ever smaller M has to stop. So there must be a minimum value of M, which we imagine will be negative. So we're going to have that beta M min times J, well, I should write it differently. I should say that nothing has to equal the mod square of J minus applied to beta M min. And when we expand that out, there'll be other things happen here. And so in other words, nothing is going to be beta M min J plus J minus beta m min. That's awfully similar to what we had here, where we had a j minus j plus. So you can see that it's going to produce the same stuff, except that the sign of the commutator is going to be different. Otherwise, everything will be the same. So this is going to be nothing, is going to be beta m min j squared minus jz squared plus jz. Which is going to lead to the conclusion that beta, nothing, is going to be beta minus m min squared plus m min. In other words, beta is also equal to m min minus 1. So we have a relationship here between beta and the largest value that m can take, and between beta and the smallest value that m can take. And we can from these, between these two equations, we can eliminate beta and learn that m min squared minus m min, which is this, is equal to beta, or minus beta equals naught, but minus beta is the same as minus m max plus 1. So we have this equation, and this can be thought of as a quadratic equation for m min in terms of m max. Right? So this is a quadratic equation, and it tells me that m min is equal to minus b, well, b is minus 1, so that's equal to 1, plus or minus the square root of b squared minus 4ac. A is 1, c's minus this stuff. So plus 4 m max brackets m max plus 1 all over 2. Looks ugly, but actually it's very beautiful, because this is going to be a half of 1 plus or minus the square root of. Well, let me write down what it is, and you can tell me whether you agree with it. It's m max plus 1 squared. If you square this stuff up, you get 4m max squared. You also get 4m max from the cross terms. 2 times 2 makes 4, so that's that, and you also get a 1, that's that. So we can extract the square root, right, because we've got the square root of a square, so we have plus or minus this. M min is obviously smaller than m max. So the plus root can be ignored, because that would tell me that m min was bigger than m max. So only the minus root is wanted, and you soon find that that is equal to minus m max. So there's a biggest value that m can take, and there's a smallest value that m can take, and we've shown that that's minus the biggest value. In other words, we've got a picture like this. We have a biggest value here, then we have a next value, then we have a next value, then we have a next value, and suppose that this is the end, then 0 lies, so this is a plot with m going up here, so here would be 0, say, in this case, this would be a half, this would be 3 halves, this would be minus a half, and this would be minus 3 halves. Or it might work out like this, that we'd start here, but the key thing, is we could start slightly higher up, and then we would have this one, and this one, and this one, and this one. So if we started at 2, we could have 1, nothing, minus 1, minus 2. These are the possibilities. But the key thing is that I know that in an integer number of steps, here 3 steps, I can go from the biggest value to the smallest value. Here there are 4 steps, 1, 2, 3, 4. So the key thing is that twice m max is an integer. Now, we could carry on talking about beta and M max, but it's extremely boring and nobody does that. What they do is they use a new notation. They say that what the new notation is that J is what you mean by M max. The biggest value of M is called J, little j. And what have we got? We've got that beta is equal to M max plus 1, that's on the board just here, is therefore equal to j plus 1. And we know that 2j is an integer. In other words, j is a half integer. It may be an even number of half integers, in which case it's an integer itself, or it may be an odd number of half integers. So in this left-hand column, j is a half integer. All the values of j is a half integer, consequently all the values of m are half integers. In the right column, j happens to be an integer, and therefore all the values of m are integers. Therefore, this beta number is sometimes an integer. So if j is an integer, this is an integer. For example, if a possibility is that j comes out being 0, in which case beta is 0, or j might come out being 1, in which case beta would be 2, or j might come out being 2, in which case beta would come out being 6. We have a sort of funny selection of integers. But worse than that, when j is a half integer, the values of beta are really quite weird. So we don't use beta as a label. So we relabel beta m to jm. Instead of using as the label in here that tells you how this state responds to j squared, instead of using the actual eigenvalue, you use this number, which is either an integer or a half integer, from which you can work out this eigenvalue, because this eigenvalue is j plus 1. That is to say, we have that j squared on jm is equal to j plus 1 jm. And we have that jz on jm is equal to m of jm. This is the new notation universally used. So we've changed notation only because we've discovered that the numbers beta are themselves rather unpleasant and don't make for handy labels, but they are related through this equation to something that's very simple, which will be an integer or a half integer, and moreover, tells us immediately what the largest value of m is that you were allowed to have. So we have, if j equals 2, there are 5 states. There is 2, 2, 2, 1, 2, nothing, 2, minus 1, and 2, minus 2. Now, what does that mean? What statement is being made physically? It's being said that if my pen has 2 units of angular momentum, well, it has j equals 2, which means, as I've said, it has, strictly speaking, j squared has an eigenvalue of 6, right? But if we call that 2 units of angular momentum, it has 5 possible orientations, right? This one, this one, this one, this one, this one, and this one. Only 5. This is what they called space quantization when Stern and Gerlach discovered this experimentally. I think it's a terrible, terrible term, right? It's not. I wouldn't call it. I think it's a very bad idea to call it space quantization. But I just tell you historically that's what they called it. But this is the bizarre conclusion that we have a discrete set of orientations anyway being possible for a pen with that amount of angular momentum. If j is a half, then what do we have? We have a half and a half, and a half, and minus a half, and that's it. Only two states. So that's why we've been talking about electrons and things, two objects with angular momentum, total with spin a half a unit of spin angular momentum, like electrons, protons, positrons, etc., as the archetypal two-state system, because there are only two possible orientations. Now, this is very misleading, right? But I've already given health warnings on this, but the naive interpretation is that your spin-a-half particle, your spin-a-half gyro, has two orientations, this one and this one, and nothing in between allowed. Okay, so that is a grossly oversimplified picture which leads to misunderstandings, but it gives us a bit of orientation, and people often do think in those terms. In the 3 halves case, we would have 3 halves, 3 halves, 3 halves, 1 half, 3 halves, minus 1 half, and 3 halves, minus 3 halves. We would have 4 possible orientations. We'd have this, 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 and this, never pointing horizontally, etc., etc., etc. Okay. Almost done. Let's have a look at the effect of rotation around the z-axis. Okay, so psi goes to psi primed, which is u of alpha of psi. So these angular momentum operators came in as the things you put in an exponential in order to generate a rotation, the unitary matrix that makes you a new system, which is the old system rotated. So we want to see what we get now. So let's see what happens when we rotate a state of well-defined one of these eigenstates here, right? So let's do e to the minus, so if we go about the z-axis, then alpha only has a component in the z direction, and this becomes, and it has a magnitude phi, so this becomes e to the minus I, phi is the rotation angle, jz, and let's use that on one of these jm states. Well, this is a function of an operator used on, it's a function of an operator, so by the definition of a function of the operator, it has the same eigenstates as the operator whose function it is. So this thing is an eigenstate of this operator, and the eigenvalue is the function on the eigenvalue. So this is e to the minus I phi m jm. So one of these states of one of these eigenstates here, when you rotate it using this rotation operator, produces you the same state multiplied by this phase factor. Okay, so if we rotate through 2 pi, if we rotate the thing completely around, so if we put phi to 2 pi, we are looking at, what are we going to call this? We're going to call this psi primed, say, right? Psi primed is going to be e to the minus 2 pi I m. Well, maybe we should say 2m pi I times what we first thought of. If m is an integer, then this is going to be a number 1. So this is equal to jm if m is an integer, but it's equal to minus jm if m is a half integer. as we know it can be. So we have the surprising result that if you rotate a system with half-integer angular momentum completely around, through an entire rotation, its state doesn't return to its original state. It returns to minus its original state. And this seems strange to us because we don't have any concrete experience. We have no experience of this kind of thing for the following reason, that particles which have half integer j, well, particles are described by fields. Particles that have half integer j are described by fields whose value never becomes, this is a result of quantum field theory, whose value never becomes large compared to the quantum fluctuations in the field, the quantum uncertainty in the field. So the values of these fields never become significant, and these fields never enter classical physics. So the Dirac field, whose excitations are electrons and positrons, is not something that's part of classical physics. It's a part of the vacuum, just the same as the electromagnetic field or the gravitational field, but it's never excited at a macroscopic level, so it doesn't enter classical physics. So we have no experience as classical beings within classical physics of the fields associated with these half-integer values of m, and therefore we're unaware of this fact that if you turn the thing completely around, it changes its sign. And the fields we do have experience of, the electromagnetic field and the gravitational field, belong to integer values of m. The electromagnetic field has has j equal to 1, and the gravitational field has j equal to 2, and therefore these fields don't manifest this strange behavior. Well, I think that is the right place to stop, even though it's a little early, and we will look at the rotating molecules as a physical application on Wednesday.